Okay, welcome back. Right, so I've given you some motivation how to think of the cigar that we want to rule out under Ricci flow. And I told you two ways to do it, either showing that you have a good isoperimetric inequality or show that you have this non-collapsing. Now, how do you prove a good isoperimetric inequality? What could you try? Hamilton tried a long time to do this directly. We're looking at the volume of small balls in the three manifold and their boundary area, and look at the evolution equation of the isoperimetric quotient where it is minimized, and none of that worked. And now, in a different course, I've shown that the isoperimetric inequality, at least in Euclidean space, is equivalent to the Sobolev inequality. Right? So, to control the isoperimetric behavior, can control the constant in the Sobolev inequality. In fact, there's an equivalence. Right? You look at the integral, say, of a closed surface, you look at the integral of g to the n over n minus 1 over the surface to the n minus 1 over n, and try to estimate this by a constant times the integral of gradient j over the surface, and you also usually have to add in a lower order term. This is the Sobolev inequality, and in Euclidean space, you just look for this constant if you have functions of compact support. Now, the point why is this related to the Sobolev inequality to the isoperimetric inequality? Well, you want to insert the characteristic function of a domain, and this becomes the perimeter, the boundary. And here you have the right power of integral of 1, the right power of the volume. And you have to make this rigorous with the co-area formula. Now it turned out it's not possible, to control this constant along the Ricci flow and so that it is somehow preserved. None of these attempts worked. And a direct working with area and volume of subsets also did not work. Now, here comes Perelman's major contribution, major idea. Perelman said you should not go for this Sobolev inequality, you should go for the logarithmic Sobolev inequality. Use the logarithmic Sobolev inequality show that a version of the famous Euclidean logarithmic Sobolev inequality by Gross exists on any manifold for any t with a constant that improves in t. That improves under Ricci flow. And then use that Sobolev inequality to show that some that sort of this Gaussian isoperimetric behavior is getting better and rule out collapsing. Use this to rule out collapsing and get lower bound on the injectivity radius. It may depend on t, but for each t you get a definite lower bound. In other words, you can use this log Sobolev inequality estimate of Perelman to solve both our problems. You can solve the problem with the non-collapsing, ruling out the cigar soliton as a possible blow-up limit of singularities, and you get the lower bound on the ejectivity radius that we need in order to prove the compactness theorem to make all the rescaling arguments rigorous. So there's one huge progress, some huge insight. There is a log Sobolev inequality that is improving under the Ricci flow, and that makes all these estimates possible. And this, of course, links then Ricci flow to the log Sobolev inequality, which was till then a completely different subject, and which is very important in stochastics, because the constant in the log Sobolev inequality, as we will see, is dimension independent, and therefore can be used for stochastic problems that are set in spaces of huge dimensions, even taking limits where the dimension goes to infinity. So this is linking different areas of mathematics that have been very distant before Perelman's work and are now all of a sudden very close and interlinked. So we start with the log Sobolev inequality of Leonard Gross. And it has to do, as you might expect, with the heat current. So first, the log Sobolev inequality. In Rn. So let d sigma be the Gaussian measure on Rn, so we take 1 on 4 pi tau. Don't think of tau as a time at the moment, think of it as a scaling parameter, e to the minus x naught squared over 4 tau, where tau is bigger than 0 and x naught is in Rn, and I often say x naught equals to 0. And this is d sigma with respect to the scaling parameter tau. And if tau is equal to 1/2, I just drop the tau. So d sigma is d sigma where tau is equal to 1/2. So there we get 1 on 2 pi to the n over 2 times e, and here I just take minus x squared divided by 2, okay, times dx. And with this measure, the log-Sobolev inequality, of course, takes the following form, theorem, cos. And it says that suppose V is a smooth function from Rn to R, and we assume that it is square integral with respect to the sigma. Then it is true that integral of over Rn of V squared times log V d sigma is less than integral the gradient of V squared d sigma plus an extra term, which is integral V d sigma over Rn times log of integral V squared d sigma. Okay, that's the inequality. And there's a number of remarks. First one is you have equality unless V is a constant. You have equality if and only if V is a constant. Secondly, this remark that I made before, why this is so useful for stochastic, there is no constant involved depending on n. And thirdly, so you could do this on an Rn and then let n tend to infinity. For example, if the Rn describes the space, the pending multiple particle system, and n is, say, 3 times the number of particles. And then the last remark is if we rescale V in such a way that the integral of V squared d sigma over Rn is equal to 1, then we just have to prove the simpler inequality where this term is not there. Then we just have integral V squared log V d sigma over Rn is less than integral gradient V squared d sigma over Rn. And if you compare this to the Sobolev inequality that one usually has with respect to the weight measure, remember that there we had a power of V which was bigger than 2. We had V to the 2n over n minus 2, which is bigger than 2. And so here in this particular case, instead of gaining a whole power on the left-hand side, we just gain a logarithm, a tiny little bit compared to the power of dV squared. Okay. Now, the this theorem of Gauss, I don't want to prove. In fact, I did explain a proof in the course I gave a few semesters back on the geometric inequalities, and I used the symmetrization method. So proof, for example, by symmetrization in the spirit of long paper by Talenti, where he also proves the other Sobolev inequalities using the symmetrization method and reducing it essentially to an ODE, showing that the optimum is attained in the rotationally symmetric setting. Then you get an ODE you can solve, and you have to use the co-area formula and the ordinary isoparametric inequality and the isoparametric inequality with respect to the Gaussian measure. So this is by now well known. There's other methods of proving it that I don't want to go into. Let's just take this for granted for a moment, and let's see that there is a completely different way of describing this Sobolev inequality. Recall that the ordinary Sobolev inequality can also be viewed as a variational problem. After all, you want to optimize the quotient. If you forget this term for a moment, suppose this has been fixed, then you want to optimize the quotient of the integral of gradient g with the integral of power of g. Say, if you have here 2n over n minus 2, you would have gradient g squared, the Dirichlet integral divided by the nonlinear power of g, and optimize this thing. So we can write this as write the Sobolev inequality as a variational problem. And that's exactly what Perelman did in the case of the logarithmic Sobolev inequality also. And that's why he introduced his W function. And the point is that you can consider this W function on a general Riemannian manifold. So Perelman said you should consider for a Riemannian manifold smooth, no boundary, and I don't require compact here. Of course, if it's non-compact, you have to make sure all the integrals are bounded. You may have to make some assumptions near infinity, but let's assume just at the moment smooth, no boundary to set it up, and some f from Mn to R smooth, and some scaling parameter tau bigger than 0. The functional W of the metric of the function and the scaling parameter, we want this to be the integral over the manifold of tau times the gradient of f squared plus the scalar curvature of the metric G, and then you add in plus f minus n, and then this whole thing you multiply with u dv with respect to G, where u is equal to what you would expect from the heat kernel, 1 over 4 pi tau to the n over 2 times e to the minus f. So u is completely determined by f and by tau. And now we want this to fit together exactly when we have the heat kernel. So we say that G, F, and tau are compatible to each other. We say that G, F, tau are compatible if the U has the right volume. If U is a probability measure, so if integral of integral of u is equal to 1. So you see the correspondence with the scaling parameter. So this is a condition relating the scaling parameter and f and the metric g all together. Right? So the scaling parameter f to g, and this is equal to 1. Now, how does this look like in Euclidean space? Now, notice that in Euclidean space, we can just compute, do this little computation, Laplacian of the heat kernel. So this is the Laplacian of 1 on 4 pi tau to the n over 2 e to the minus, and the heat kernel here, the f. So in Euclidean space, the f would be x squared over 4 tau. It's the logarithm minus the logarithm of the heat kernel. So if you take the Laplacian of the heat kernel in Euclidean space, you end up with, let's do the calculation, di, and you get here minus xi over 2 tau times u. And then this is equal to x squared over 4 tau squared. And then if you differentiate this, and if you differentiate this, you get minus n over 2 tau times u. So the integral of the Laplacian is equal to 0. So in Euclidean space, we get that this important formula, n over 2 times integral u dv, which is integral of u, this is our n. The integral of the heat kernel is 1, so we have n over 2 is equal to the integral of x squared over 4 tau over Rn times u dx. And this, of course, is the same as the integral over Rn of the gradient of f squared times tau times u dx. So this term here is exactly the thing that comes up in the w functional here. In Euclidean space, r is equal to 0, and the integral of f, so you get therefore in Rn we get that the w with respect to the standard metric with respect to x squared, the logarithm of the heat kernel, x squared over 4 tau, and tau, that this thing is integral tau df squared, so this is n over 2, is the first term, plus 0, and then we get the integral of f, this is the integral of x squared over 4 tau times u dx, and then we get minus n, and integral x squared u over 4 tau is n over 2. So we get n over 2 plus n over 2 minus n is exactly 0. So the w functional is exactly equal to 0 on the heat kernel in Euclidean space. And now we are ready to reformulate the gross Sobolev inequality by just saying that in Euclidean space, this thing is greater or equal to 0 for any f and any tau, and with equality exactly when f is equal to the logarithm of the ordinary heat current. Okay, so we have the proposition suppose G equals delta is the flat metric on Rn, standard metric, and f is equal to an f and delta f and tau are compatible. It's such that 1 is equal to 1 on 4 pi tau to the n over 2 into your e to the minus f dx over Rn. Then W of G of delta f and tau, W delta f and tau is greater or equal to 0 with equality if and only if f is equal to x minus x naught squared over 4 tau for some tau greater than 0 and x naught. Alright. So the point is that the this statement that W is greater or equal to 0 for all f is just exactly equivalent to the logarithmic Sobolev inequality on Euclidean space. So proof show that this inequality star is equivalent to the logarithmic Sobolev inequality of gross. Now, for that matter, we have to relate our f to the W. To do that, to make life a little simpler, notice that the in Euclidean space, the W has just a, or actually in any case, the W has a general scaling invariance. Notice that W has the scaling invariance in the sense that if I take some f, some g, and some tau, and I rescale the metric exactly the same way as tau, then I get the same thing. So I get the same, if I divide here by tau, so I get 1, and I divide here by tau, I get the same thing. So in particular, it is enough for this to prove this inequality for one particular tau. So it is enough because if you take tau times the Euclidean, the flat metric, you still have the flat metric. So it's enough to prove the inequality for tau equals 1/2. I.e., we divide this by 2 tau. We just have to prove that 1/2 tau times delta times f times 1/2 is greater or equal to 0. And then it is also true for this one here. Right, and this means I have to see 1, 5, 6. Right. Okay, so now for tau equals 1/2, then we should look at the compatibility condition. F is compatible to tau equals 1/2 if then in the denominator here we get 1/2 pi to the n/2 times the integral of e to the minus f dx over Rn is equal to 1, right? That's now the condition for compatibility. And now we have to find the right v that we want to apply the gross log Sobolev inequality to. So then set v to be e to the, and now we take, instead of minus, we take x squared to the 2. That's what we expect f to be, minus f. So we want f to be, in the end, in the equality case, we want f to be x squared over 2. So let's set up v to be the difference. Actually, we take squared over 4 and then f over 2, which is the square root of what I wrote down. Okay, so take this, and then a quick, let's see what the measure v squared d mu is then equal to. So then v squared, our old measure d sigma, this is now squaring v, we get x squared over 2 instead of over 4 minus f. This is v squared, and then the measure d sigma was 2 pi to the minus n over 2 times e, and here it was minus x squared over 2, and then times dx. And now the way we set it up is that the x squared terms cancel out, and we have 2 pi to the minus n over 2 times e to the minus f dx. So our condition, our compatibility condition for f and tau equals 1/2 just relates to the fact that integral v squared d sigma is 1. We have integral v squared d sigma is equal to 1 over Rn, and therefore we can use the log Sobolev inequality in the simplest form that I had for the remark. So log Sobolev then says that integral of v squared log v d sigma over Rn is less than integral gradient v squared d sigma over Rn. So I'm using the log Sobolev inequality of course to get this, and now I just have to do the computation. So what is the left-hand side? Left-hand side in this inequality, I have to take v squared, so I get the integral of e to the minus f again, because v squared d sigma is just this thing here, and then I still have to multiply with the log, and the log of v is this term up here. So I get this term up here, x squared over 4 minus f over 2 times v squared d sigma is equal to 1 over 2 pi to the n over 2 times e to the minus f dx over Rn. That's the left-hand side. Exactly. Now to compute the right-hand side, now also that computing the gradient of v, I get gradient of v is equal to xi over 2 minus gradient if over 2 times v, and then I get that gradient of v squared is equal to x squared over 4 minus gradient if xi over 2 from the cross term plus gradient f squared over 4 times v squared. So the right-hand side turns out to be well, the integral of gradient v squared, and then we get again here v squared d sigma. This measure is what we had before, so we get just the integral over Rn of x squared over 4 minus gradient if xi over 2 plus gradient f squared over 4 times v squared d sigma, and v squared d sigma was this measure up there, so this is 1 over 2 pi to the n over 2 times e to the minus f dx. So we have sort of the right same measure here on this side and on this side. Now, you see, on both sides you have x squared over 4, so we can ignore this term. And this term here, we can integrate by parts. You do the integration by parts. So note that integral minus di f xi over 2 times 1 over 2 pi n over 2 e to the minus f dx, integrated by parts, then we get a plus sign and another minus sign from here, so we get back to minus, so we get let me see. Oh, right. No, I can write this minus gradient IF of this. I can write this as 1/2 xi times gradient I of e to the minus f times 1 over 2 pi to the n over 2. Because di of e to the minus s is minus dif times this, so I can write this, and then the integration by parts, I notice the fact that di of xi is n. So throwing it on here, I just get n over 2 times the integral of e to the minus f, but this by the compatibility condition that is equal to 1. So I get n over 2. And then you see that you just multiply everything by 2, and then you see from here it follows that w, which is equal to w of delta f 1/2 is just equal to the twice the right hand side times the left hand side. And this is greater or equal to 0, proving the theorem. Okay, so the log-Sobolev inequality just says that on Euclidean space, the W on all compatible functions is at all scales greater or equal to 0. So it's a very nice formulation of the log-Sobolev inequality as a variational problem with a functional that Perelman has generalized in a natural way from Rn to all Riemannian manifolds. And then next time we will see how this W also arises naturally from the heat equation. It has to have something to do with the heat equation because the heat kernel is involved. So it turns out it's something like the derivative of the entropy under the heat equation. And the amazing thing is that then we get a monotonicity formula for this W if we have a solution of the adjoint heat equation together with Ricci flow. And that'll be the basis for the non-collapsing estimates later on. Okay, thank you for today.